Hi, I'm David Baraton from the Department of Chemistry at Duke University, and I'd like to tell you about how one of the great discoveries of the 20th century in physics and chemistry intersects with biology. So one of the great discoveries of 20th century physics and chemistry was the dual nature of matter, the fact that very small, very light particles sometimes behave as waves and sometimes as particles with mass. And this discovery explains much of chemistry. It explains the structure of the periodic table, the stability of atoms and molecules, the nature of the chemical bond, and all of the consequences of those rules. There are other profound signatures of the dual nature of matter. So for example, if you take a molecule, even a large molecule like buckyballs, C60, and you throw them at two very closely spaced slits, you'll measure diffraction patterns as those particles move through the slits. That's a wave characteristic of matter that is predicted by quantum mechanics. I mentioned that quantum mechanics dictates the structure of the periodic table, the nature of the chemical bond, but you could ask, what does that mean for life? Can I just take the rules of the chemical bond, the rules of bonding as derived from quantum mechanics, and then use those rules to construct effective classical models for nature? This does work relatively well. In fact, there's a whole software industry devoted to classical molecular dynamics applied to molecules and to biological structures. This area works in drug discovery and drug design. It explores the function of molecular machines and the nature of biological processes. But there's some phenomena where these classical or effectively classical models fail in a profound way, and that has to do with biological energetics. So in biology, there's a narrow window of energy, approximately 2.5 electron volts wide, that applies and governs bioenergetics. So what's an electron volt? Probably your first question. An electron volt is the energy that an electron acquires when it's moved through a 1 volt potential drop. So there's a window in biology about 2.5 electron volts wide where the processes of photosynthesis and respiration occur. It's very important that the processes that occur in this window deliver their particles to the right places at the right time so as not to waste energy or cause biological damage. So it turns out that biology needs to move electrons within this energy window with great precision. The electrons that move in this biological window move by quantum mechanical tunneling through an intrinsically non-classical process. So imagine an electron that's bound to a molecule involved in these biological energetic reactions. If this electron were purely classical, it would sit on those relevant molecules. On the other hand, a quantum mechanical electron is not so well localized. It has a propensity to leak away from the places that classical mechanics suggests it should spend its time. And it's this very weak leakage of the electron probability away from the places that it spends most of its time that enables reactions in bioenergetics to occur. So the proteins in biology actually facilitate this electron tunneling, this non-classical motion of electrons away from the regions where they spend most of their time, and facilitates the processes of molecular bioenergetics. Now, how they do that in detail is the subject for a future lecture.